Hello, everyone. I'd like to welcome you to our webinar, Adopting AI in Optical Networks. My name is Hebe. I'm the Communication Specialist of Huawei Transmission and Access Network product line. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your control panel. I'll bring them up during the presentation, and we'll also have time for questions at the end. Now, we'll turn the time over to Dr. Christopher Janz, our presenter today. Dr. Janz is Technical VP of Huawei Canada's Optical System Competency Center. Hello, Chris.
Hello, Hebe, and welcome everyone. Good morning, good afternoon, good evening, wherever you may be. Thank you for joining us. The topic today, as Hebe said, is optical intelligence and applying that to maximizing network operations efficiency. And perhaps a good place to start is what do we mean by intelligence in this context? And thinking about that, I think the right way to put it is the role of network intelligence is to deliver information that's needed to support operational decision making. Okay, and there's really two uses or contexts for using such information. The first is really about enabling the best operational decisions. It's the idea that the more accurate, the more timely, the more case specific the information intelligence we synthesize, the better the quality of the operational decisions we can make. And that leads to improved operational outcomes, whether we're talking about improved resource efficiency, service quality and integrity, or even revenue and profits. And we could call this idea of improving operational outcomes with better information, we could call that optimization. Of course, the second aspect is automation, right? So if we've used concepts like SDN, et cetera, to, if you like, softwareize the operations of the network, we place control of the network state much more substantially in the hands of software. We can go from policy to action through software, provided we have this decision-making information synthesized in software, really to marry to policy, determine actions to be taken, and allow an action loop to be closed. And automation is really all about minimizing operational cycle times, minimizing errors and costs that are associated with manually intensive processes. It's an OpEx sort of proposition. And the marriage of the two, I like to call that autonomy, where we get both outcomes: minimize CapEx and OpEx, maximize service quality and velocity of delivery, and revenue and profits. So as you see, there's really two pillars. The first is general softwareization of network control, and the second is network intelligence that's synthesized in software. Now, how does this work architecturally? Well, there's really three components to this scheme. The first, in the physical network itself, we're bringing intelligence there. First of all, that's through an enhancement of ASON. We call that ASON 2.0, where we're bringing greater compute power, able to support larger scale network operations, where we're looking to improve ASON processes for faster provisioning, self-healing, and also we're bringing progressively new kinds of optical sensors to the physical network. And this is very important, as you'll see. Typically, we've had alarms that look for significant degradations of service. But really what we're talking about here is bringing measurement capability that's directly relevant to the optical physical platform. Measuring powers, OSNRs, things like that. We'll touch more on that later. The second component is, let's call it the brain. In our product language, that's Network Cloud Engine. This is the cloud-based platform where we measure management functions with control and analytics that can create that closed loop operation, and where we have all of our scenario-based applications that enable zero-touch operations. And associated with that is something that sometimes we call digital twin. This is really the cloud-based adjunct associated with NCE, where we have really our optical intelligence synthesis functions going on. Right? So that's a series of algorithms and models. It's big data, so it is a data platform, among other things. It's the home for a collection of these new types of optical sensors in the network, and plenty of computing power that's optimized for AI functions. So a few examples. If we look at use cases, we can consider things like the following. Resource prediction. So what new network elements and other resources will be required where and when to quickly support new capacity and service support on the network. Smart commissioning, right? Heading towards zero touch even at the optical layer. How do we know that when we press the button, things will come up as expected and within parameters? Network health prediction, right? So understanding closely the performance of optical services on the network, how they may be evolving and why, and the ability to extrapolate that so we can, if you like, preemptively act in the face of the approach towards seriously disturbing degradations. And going along with that root cause analysis, how can we automate that, right? So we can understand exactly what the sources and locations and explanations for various types of degradations are without a lot of manual effort. And if we look at the kinds of algorithms we need to support various functions like this, we see that, well, on the one hand, there's fairly classical methods like time series analysis and prediction, regression. But there's also, if you like, new flavors of algorithms that are largely in the machine learning or AI camp, things like neural networks, aggregation, and clustering. And we'll show some examples. Big data collection, of course, is part of this. As I mentioned, NCE and digital twin are a big data platform in the cloud. And of course, the idea is that we're moving from collection of relatively limited sets of alarms to more continuous collection of ongoing sensory data of various types across the network with faster sampling. And going along with that is an increasing use and embedding of AI-capable computing power. Now that's both on physical network elements, right? For example, so that we can pre-process some of the sensory data to minimize or reduce the streaming of that information into the cloud platform, but also on the cloud-based platform itself, where we're leveraging AI-capable processing technology to get better results. Now, as I mentioned, autonomy is really a life cycle automation idea, right? Where we're moving in a continuous loop from planning, deployment, and provisioning through ongoing monitoring, assurance, and analysis in a closed loop. And there's different categories of, let's call it use cases or benefits that we target with this kind of functionality. The first you could classify among different ways of binning these things. You could classify in a revenue attack category. And these are things like OVPNs and premium private lines for enterprise, where we are supporting automated service provisioning, even handing over control of dynamic service provisioning directly to customers. Supporting plug and play with customer premise elements, sophisticated SLA assurance, and of course, mass customization, if you like, of services along various dimensions, connectivity endpoints and bandwidth, but also latency controls, latency targeting, and restoration performance targeting. A second category is all about low-touch maintenance, and this is directly an OpEx target. It's things like clear health visualization health prediction, automated troubleshooting, RCA, as we discussed, and smart commissioning. And a third category, I think you could call generally planning. Another name for at least part of that is network resource assurance. This idea that we facilitate getting a clear and accurate understanding of resources on the network, how they're being used, the trends on service and capacity utilization, the ability to predict needed physical element accretions to the network, and automated recommendation of planning for pre-positioning, deployment, and service turn-up on those resources. Now, I think at this point, Hebe wants to do a poll.
Okay, let's start the poll now. The question is, which areas would be your priority for adopting optical intelligence in your networks? Number 1, advanced private line service delivery. Number 2, service configuration automation. Number 3, network health troubleshooting and fault prevention. Number 4, capacity and resource planning. Could you please select? And much choices are available. Okay, let's have a look at the most people select network health troubleshooting and fault prevention. And the second is service configuration automation. Do you have any comments for this one, Chris?
No, just that this is pretty consistent with, I think, what I hear from customers. Some are particularly concerned about provisioning automation, the move toward zero touch. In many customer cases, premium private lines, no VPNs, as a needed support to growing demands is pretty important, and many others emphasize the lower zero touch maintenance with the various health management features trending toward better accuracy and lower manual process. So yeah, I think pretty consistent with, what I see in the field.
I also heard many of customers, they said troubleshooting is very important for them. If they can know what will happen before the trouble occurs, it will be much better.
Right.
Okay, let's continue.
Okay. So now let's look at a few of those examples in a bit more detail and talk about optical service commissioning, really trying to take it from the status quo where, of course, wavelength coupling, which means various optical services that pass through the same amplifiers. The amplifiers couple, if you like, the behaviors of those co-propagating signals so that when we turn up a new service, extinguish or reroute an existing service, there are impacts to other services propagating through the same amplifiers. So that introduces a complexity and an element of risk. Of course, there's always the question of the performance from a noise and ultimately BER perspective on a service that we're about to turn up. This tends to require a certain degree of skill, expertise, and caution, which leads to low time efficiency or slowness of process. And really what we're trying to get to is through the synthesis and application of the relevant intelligence toward, first of all, a de-skilled process where it's software that's telling us what we can do and what we can't. That trends toward, let's call it safety, zero interruption of services, and high efficiency. We can now move directly to much faster automated actuation of service commissioning. And this depends on things like, particularly because amplifiers are the source of the coupling of behaviors among channels, having very accurate models of EDFA behaviors that we can use to accurately model the implications on power variations among channels, but also the evolution of noise and ultimately DER on new channels or adjacent channels, and then using that information to generate very smart batching and sequences, and ultimately for parallel actuation of state changes across the network. And that's what gets us our acceleration of actuation of conditioning state change. And of course, as in the general picture here, most of this intelligence and calculation, this happens in the brain, but we rely on the nervous system of the network, and that's really the WSON control plane, to drive the actuation once the trigger is given by the network brain. Health prediction and this trend toward proactive O&M. Of course, on the optical network, yes, we have some hard and rapid onset faults like fiber breaks that are difficult to predict, and we've got long-standing mechanisms to simply react to those kinds of faults. But of course, many faults are in fact degradations that have gotten worse over time and that have various sources. Anything from laser wavelength or filter drift to degradation of fiber, whether that's through the accumulation of losses over time from splicing or reconnect operations to physical degradation of the fiber. So in general, the troubleshooting of faults, what exactly is going on, where is it happening, is difficult to discern, and especially difficult to discern early when some of these degradations are at early stages. That leads to high OPEX. In fact, we have one carrier partner in China that estimated that this kind of troubleshooting occupied more than a tenth of their total OPEX. Really, so the category of function we're trying to create here would take us toward the fact of being able to use software to detect early and then appropriately classify and localize degradations of different types and sources, and then be able to monitor them and look for trends, to classify their severity at any point in time, and to look to when they may become critical and to suggest the appropriate proactive response before criticality is reached. And with this kind of effective function, we estimate in partnership with carriers we've worked with that the impact on operations costs, let alone disturbances to customer services, could be very high indeed. Now, this is really a true big data problem, right, where we're essentially performing an automated diagnostic function similar to what doctors do in their practices, right? So we have all of this sensory information from the network feeding up into the cloud, and we're using machine learning built models that pass all of this sensory data and have learned to discern the signatures of different fault types. Again, very similar to what a doctor would do, right? You go to a doctor, you say, I have a fever. He'll say, well, do you also have nausea? He'll take your blood pressure, pulse, check your breathing, and he'll look across the severity and the order of presentation of these different symptoms to try to figure out exactly what's wrong with you. It's the same idea here, right? So we've done work with a number of customers on live data from real networks, where we also have the final classifications and localizations of degradations and faults to support learning, to produce algorithms that in fact are capable of this kind of classification by type and severity of degradation or incipient fault. And ultimately that will lead us to the ability to recommend preemptive or proactive maintenance steps. One of the things that we need to understand well, both for provisioning automation and for health prediction, where we may be interested in both what is the current state of health and why, what ought it to be under better or more ideal circumstances, is the ability to accurately model and predict the performance of services on the network. This is a very complex problem. It's something that we've made a lot of progress on in research. A simple picture here. If we want to understand not just bit error rate, but margin on a service, we need to understand first what is the baseline, the back-to-back performance of the transmitter-receiver pair, right? So in the absence of impairments on the connection, what would be the native performance on that circuit? Of course, in general, a transmitter and receiver will never have been tested directly back-to-back together. So we have to find ways to, at point of manufacture, measure specific data on each in a way that they can be brought together subsequently in a model to generate the back-to-back performance estimation. And then we have basically 5 categories, or 4 categories of impairments: effect thresholding, optical signal to noise, so noise generated in amplifiers, nonlinearity or nonlinear noise, PDL, polarization dependent loss, and penalty due to filtering. And in all of these cases, we need a couple of things. First of all, we want to put as much ability directly to measure these things into the physical network as possible. The more we can directly measure, the less we have to model, and the better our results are going to be. But in all cases, we need models as well, such that with whatever available information we have, we can get good estimations. As an example, as I hinted earlier, we've done a lot of work on EDFA modeling. We've figured out ways to construct fixed neural network-based models for gain and noise figure performance that are customized for each in the final model results for each amplifier instance through the application of a per amplifier baseline measurement that's taken at the point of manufacture and recorded on the ROM for each device. That's something we use for power estimation for commissioning, but also for noise assessment. As a second example, filter penalty impacts. Here we need 2 things. First of all, we need to be able to measure in the field the net filter shape on any particular path, and that's capability that we're developing. And we need a model, and here 2 neural network models have proven to be a good vehicle to take us from a measured filter shape to bit error rate, Q or margin impact of that particular shape. And on the lower right, just some examples showing across many measurements that we can in fact get very good correlation between the model results and the measured results. What's another way we can use this beyond provisioning? If we look to the planning problem, where we're trying to squeeze as much capacity utilization out of the network as we can, one thing that we found is that, of course, if we go from fixed grid, fixed transponders to flex grid, we're able to get a capacity improvement on the network. But we've also found that if we go beyond flex grid and to flexible transponders, that is where we're able to to the modulation rate, format, and coding, we are, in a sense, to make that also flexible, settable parameter. We're able to get even more capacity out of the network. And what's shown in this graph is a measure of congestion with the optimal network solutions across all of these parameters for a particular case, which is on the left. So the farther from congestion 100% we are at a given capacity, the better, the maximum or the most remaining capacity to be used on the network. So, how is that possible? Well, it's really, of course, the idea that with flexibility and transponder setting, we're able to trade capacity or transmitted capacity for reach. Right. The more we try to put through a particular bandwidth, the less the reach. We understand that, and it's exploiting that really gets us the better results. But of course, if all we have is a default table of reaches, default meaning conservative, that is, in general, you're always going to get at least this much reach. It's not an accurate answer for any particular path on a particular network. We're going to be leaving some capacity on the table. Now, if we can substitute those reaches when we're doing these operations, planning operations in real time, with accurate reach answers on particular paths that are delivered by intelligence capability, then we will get to, if you like, network-specific planning that will get us much closer to the actually available capacity on the network. And this can be ongoing and active, something we call margin management or margin compression. And of course, the more capacity we can squeeze out of a given physical network, the more efficient we're going to be on CapEx. So just to show things in action a little bit, a few views from the product interface. Here's a particular view showing statistics on fiber health, optical channels, and services. For cases that are, for example, showing some criticality or incipient criticality of performance, we can go to our embedded application table and look for example, provisioning options that will give us performance improvement in particular cases. And here's a little bit of a view of a window there where we've looked to work on a particular optical channel with degraded performance. The application identifies the optical channels that are similarly affected because they are on shared optical multiplex section portions, recommends alternative provisioning parameters and runs those through the model to predict the resulting performance. Here's an example showing a topology capture of a particular part of the network in a particular service, and we can go in and click on the abstraction view to get a resolved physical view of the actual physical resources involved. And here's the, for example, the amplifier chain involved on a particular service, and we can go down and click on, for example, a particular amplifier. And the simulation capability here is telling us what the OSNR on a particular channel is at the output of that particular amplifier. And just in another case, we're simulating here all of the paths on an entire network to get statistics on optical signal to noise ratio variation across or evolution across all of the service channels commissioned across the whole network. And on the lower right, this is some assessment of performance. This is lab-based results on OMS with, I think, 10 amplifiers and a whole host of configuration changes with different channel states, pre and post configuration, comparing the modeled and resulting OSNR changes on observed channels. Can you still hear me?
Yes, we can.
Okay. Okay. I apologize, something came through there. I just wanted to check you could still hear me. So as you see, in general, we're well within 1 dB of model versus reality analysis in our evolution across these cases. Okay, resource assurance. This is the last one I want to touch on. Of course, one of the issues we have broadly in optical network operation systems is we don't, or it can be cumbersome, we don't always have an accurate view of the resources in the network, how they're connected, and how services map to the deployed topology. And it gets further complicated as we try to add planning generated data into the picture. In the emerging system, that problem is taken away. First of all, the model-based NBIs give us a clear automatic linkage from the network up of the resource and topology state. I'll cover that in a moment. But basically, we move from the database of record being the network itself to also being in software, right? So we've got that real-time sync of resource and the resource visualization capability. When we talk about resource assurance, we're talking about moving from that to an ability to predict first the required accretions to the physical network to support predicted traffic and service growth, right? So we're relying on algorithms to take inputs on service planning, but also to study the evolution of service and capacity trends to make these predictions, basically to tell us which resources, where and when ought to be placed into depot for rapid deployment in the field, trying to get those answers as accurate and timely as possible. And the third step is also going beyond that to recommending the provisioning operations that ought to happen once those particular resources are delivered to the field and turned up, right? So we're looking at the policies that may be set to govern capacity expansion and service provisioning, through to recommendations that are auto-generated and can be enabled simply by a button push. So I mentioned this idea of abstraction-based NBI, so let me touch on that quite quickly. This has been an important aspect of the community development of SDN as it relates to the transport field, where really what we're trying to do is move from a legacy state that is something like this. I call it a closed solution, but it really means it's just a fractured vendor and operator system environment where there is no, if you like, standard interface between a vendor system and the operator system environment. There may be very little commonality among operator system environments themselves. The result of which is, first of all, we've got a very cumbersome state for the development, maintenance, and change of provider operation systems. Swapping vendors is a very big deal. The integration of new equipment or vendor capabilities is difficult and time-consuming. But also, we support very low levels of abstraction from the network up to the provider system. So really the provider system, the OSS, is staring at the full native complexity of the network. And that places the burden of responsibility on that OSS at a very high level. What we've been working very hard as an industry to get to is a much more rationalized and standards-based open environment that looks something like this, where we have standards-defined, model-based, abstraction-oriented northbound interfaces that we can use to connect vendor systems, software systems to provider systems. And those interfaces will look the same regardless of vendor. That stabilizes the environment for the software environment for the provider. But also because these interfaces are abstraction oriented, that means that they can, if requested, present the raw total native topology or inventory to the OSS, but they can also present whatever degree of controlled abstraction of view is required, right? So basically this allows the provider system to determine provisioning operations on a much more rationalized level, right? It doesn't need to understand the full complexity of detail, and it doesn't see any difference in appearance from one vendor's network to another. It's basically dealing with provisioning at a high level of abstraction. And this is something that's been supported by a very successful development in standards in the IETF under the ACTN framework. Most of the key pieces are now published RFCs. And it's something that's seen extensive testing and evaluation and proof in the field. We've been involved in such work with other vendors and a number of customers. This is just an example from 2018 that we did with China Mobile and one of our peer vendors using ACTN NBI. And we evaluated a large number of transport use cases and resolved support for everything from multi-layer topology discovery to multi-domain service commissioning, for example, Ethernet services of various kinds, looking at protection and restoration operations, and dynamic service modification. So this aspect of softwareization, if you like, of systems is approaching quite a mature state. It's something that, in terms of the standards-based NBI, is supported on our product and increasingly across vendors. One last thing I'd like to say, obviously, you can think of network autonomy as a destination, a place we'd like to get, but it should also be thought of as a journey, and it's one that is both controlled and won't happen overnight. Right? So here's just one possible view of how this could evolve. I think in every particular operator, there will be a somewhat different path, but basically we can separate the notions of information synthesis, analysis, decision-making, and actuation. We can separate these things and place manual steps at whatever point in the process we want until confidence is built and capabilities are developed. And then further, we can separate these across use cases, right? So things can go step by step and under operator control and following the operator priorities. But of course, with every step taken, we get a capability that can be leveraged, and we get one step closer to where we want to be in the end, which is a fully autonomous set of network operations. Right, so that's the end of my presentation. I hope that was useful.
Thank you everybody for your join, and thank you, Chris, for your great presentation.